Welcome to first video of first chapter for class 12 physics, electric charges and fields. This is an introductory video in which we will study about electric charges and its properties. This is your channel YouTube e-learning. If you are not yet subscribed, please subscribe to it. In first few chapters of class 12 physics, we are going to study about charges. In first two chapters, we will study about charges at rest. That is electrostatics. From chapter 3 onwards, for few chapters, we will study charges in motion, that is electric current. So first we will study about what is electric charge. The discussions about charge was there from 600 BC onwards. The word electricity is coined from the word electron. There is a Greek word which means amber. Greeks knew that when amber is rubbed with wool, gets a property to attract small pieces of paper. That is, some suitable materials like amber and wool, glass and silk, when rubbed, get properties of attraction and repulsion. So there are some material which show properties of attraction and repulsion when they rubbed. We are familiar with another example that we may practiced or done in our childhood days. That is, when comb passed through dry hair can attract small pieces of paper. This became an interesting subject, and as a result there were number of experiments conducted based on this. And these experiments suggest that there are two kinds of charges exist, and it is also found that like charges repel each other and unlike charges attract each other. So there are two kinds of charges and they call it is positive and negative. There is some property which differentiates the two kinds of charges, and it is called the polarity of charge. So there is always an interest to understand which one will be positive and which one will be negative when two suitable materials will rub together. When glass rubbed with silk, conventionally it is taken that glass gets positive charge and silk get negative charge. So how it happens, that is another question that we need to answer here. So there is a finding that loose bound electrons in one will go to the other when they rub together. So let us understand it by drawing a figure. So I am going to draw a glass rod, and this glass rod is rubbed with silk. So I know this is glass rod and this is silk. So when this glass rod is rubbed with silk, These free electrons from the glass rod will move to silk and makes this silk negative and this glass rod positive. So glass rod contains some loosely bound electrons and these electrons will move to silk when it is wrapped. So glass rod becomes positively charged and silk that becomes negatively charged. So we can say that this charge is a basic property associated with elementary particles. So let us understand this one. So what happens when a glass rod is rubbed with silk? The loosely bound electrons are moving from glass rod to silk. So electrons are moving. As a result, a momentary electric current is created, and this electricity is called frictional electricity. This is frictional electricity because when rubbed, electrons are moving from one body to the other, causes a momentary flow of charges. So one method of charging a material is by rubbing it with a suitable material. So in that case, what will happen? Loosely bound electrons will move from one material to the other, makes one material positively charged and the other negatively charged. The second method to charge a material is by making contact with a charged material. What happens when a charged material is made in contact with another material? Let us consider a material A which is negatively charged. What happens when it makes contact with another material B? Some electrons from A will move from A to B, that makes B negatively charged. So B gets charged by making a contact with the charged material A. Look at, in this case, both A and B are having same charge, and that is the charge of A, that is the charged material. So if A is positive, what will happen? A and B are also positive. If A is negative, A and B are negative. So it is having the same charge, that is the charge of the charged material A. Now, what happens to the charge of A? Since some electrons from the charged material A are moved to material B, so the charge of A decreases. So in this method, B gets charged, but charge of A decreases, and A and B are having the same type of charge. Now the question is, how much charge will be transferred from A to B? The answer is, that depends on the materials, size and shape of bodies A and B. Now we are going to understand the third method of charging a material, that is by induction. In induction method, the charged body is not made in contact with the other body. So in this case, charge of charged body is not decreased or lost in the process. Let us understand this method. Take two metal spheres A and B and make it in contact with each other. So this is A and this is B. In the second step, place a charged body near to these two spherical metal bodies. So for an example, I place a positively charged body near to the metal spheres. So in this case, we place a positively charged body near to these metal spheres. As a result, the opposite charges, that is negative charges, will be attracted towards the positive charge, and the like charges, that is positively charges, are repelled. As a result, the negative charges will come close to the positive charge, and positive charges will move farther away from the positive charge. So it will be placed as shown in this figure. So now in the next step, what we are going to do is, we will make a small separation between these metal spheres by keeping the positively charged rod there itself. So we are making a small separation between these two, and the figure will be like this. So now remove the charged rod from there and increase the separation between metal spheres A and B. We can see that the metal spheres A and B got charged oppositely, and the charge will be distributed evenly on the spheres. So in this method, we got two materials or bodies got charged. One is negatively charged and the other is positively charged. But we didn't make any contact of the charged body with these metal spheres. As a result, the charge of the charged body does not lost or decreased in this process. So the metal spheres A and B are oppositely charged. So here the charged rod does not make any contact with the metal spheres, so its charge not decreased or lost. Now let us move back to our examples of frictional electricity. We understood that when amber is rubbed with wool, amber got a property to attract small pieces of paper. Also, we know a familiar example we discussed here is when a comb is passed through dry hair, it got a property to attract small pieces of paper. In both these cases, we know amber or comb got charged, but paper didn't got any charge. Then how these paper pieces are attracted towards these charged bodies? Now we are going to explain that phenomena. So we are placing a charged body. Let's consider the charge of the charged body is positive. So a positively charged rod is placed near to a piece of paper. What will happen? The negatives, that is the opposite charge, will come close to the positively charged body and positives will move farther away from this positively charged due to the repulsion. And now the center of negative charges may be here and the center of positive charges may be here. So the center of negative and positive charges are separated by a small distance between them. Also, the center of negative charges are close to the positively charged body and the center of the positive charges are far from the positively charged body. The force is more if the charges are placed close to each other and the force are less if the charges are placed far from each other. So the force between the positive and negative will be more here than the force between positive and positive. So force of attraction here is more than force of repulsion. So what will happen? The body will be attracted with more force than the body that will be repelled. So if the particle that is like a small piece of paper, it is very light, so it will move towards the charged body. So even though the small piece of paper which is not a charged particle, it got attracted towards the charged body. That is why we observe such phenomenon in the previous examples. Now we are going to understand a point charge. In electrostatics, in most cases, we will consider point charges. What is the importance of a point charge? In point charge, charges are assumed to be concentrated at a point in space. So, this makes us or helps us to do our problems more simply, or this helps to simplify many situations. But what is a point charge? We can easily say this is a point, but whether this is a point, and I can easily say this will also be a point if you look far away from that. To understand it, imagine a picture of a football which is taken very close to it and taken very far away from it. As it goes far away from it, the size is observed to be very small, and then it considered to be a point when the distance is much far away from it. So the point means that depends on the distances. So here in electrostatics also, a charge can be considered as a point charge if sizes of charged bodies are very small compared to the distance between them. So in electrostatics, a charge is considered to be a point charge if its size is very small compared to the distance between them. So, if distance is enough, we can consider every charge as a point charge. So, in most cases of electrostatics, we will consider charged bodies as point charges. So now we are moving to the basic properties of electric charges. There are three basic properties of charges. They are additivity of charge, 2. Charge is conserved, and 3. Quantization of charge. So let us understand each one. First, additivity of charge. That is, charges can be added like real numbers. So total charge in a system is always the sum of the individual charges in that system. So let Q1, Q2, Q3, etc. up to Qn are n charges inside a system, then total charge Q is equal to Q1 plus Q2 plus Q3 plus etc. plus Qn. So the total charge of a system is always the sum of the individual charges, and the charges can be added like real numbers. This gives an idea that charge is also a scalar quantity. So charge is a scalar quantity like mass. But remember, mass can only take positive values, but charges can take negative values also. So total charge of a system is always the sum of the individual charges. Let us consider an example of this case. Let a system consist of 5 charges. Q1 is equal to minus 3, Q2 is equal to minus 2, Q3 is equal to 4, Q4 is equal to 1, and Q5 is equal to 3. So the total charge of the system is minus 3 plus minus 2 plus 4 plus 1 plus 3, that is equal to minus 3 minus 2 minus 5 plus 4 minus 1 plus 1 0 plus 3, it is 3. So the total charge is the sum of the individual charges inside that system. That is the first property, that is the additivity of charge. Now let us move to the second property, that is charge is conserved. Charge is conserved. What do you mean by conservation? Conservation always tells us that the total or net in an isolated system always constant. So remember here the charge. So net charge in an isolated system is a constant. That is the conservation of charge says to us. What is an isolated system? Isolated system may consist of some group of bodies. some may be charged bodies, some may not have any charge, like that. But the total or net charge of that isolated system is always constant. That is, it is not possible to create or destroy net charge in an isolated system. So, in an isolated system, we cannot create or destroy net charge. Remember, we can create or destroy charge of a particle, but as a system the net charge is always remains same. Remember our cases of friction as an example of this. We know a glass rod is rubbed with a silk. What happened? The loosely bound electrons from glass is moved to silk. That makes glass rod positively charged and silk negatively charged. But what happens as a system that includes both glass and silk? This isolated system of glass and silk, the net charge is always constant. That is not changed. Look at the example of charging by contact, in which we know a charged body is placed in contact with a material. So, I placed a charged body placed in contact with this one, and this charge is moves from this body to here. The total charge of this isolated system remains constant. We can make the particle charged or destroy the charge of a particle, but as a system the net charge remains constant. This is the second property, that is, charge is conserved. We can see that in all examples we saw here, this property is followed. And now we are moving to the last property, that is quantization of charge. What do you mean by quantization? The quantization concept always says that total is an integral multiple of a base unit. So, in this case of quantization of charge, the total charge is an integral multiple of a base unit, and the base unit here we call this E. So, I can say the total charge Q is equal to N into E, where Q total charge, N integer, and E the base unit. Here the base unit is charge of an electron or proton. Conventionally, charge of electron is taken as negative and proton is taken as positive. And the value of E is equal to 1.6 into 10 raised to minus 19 Coulomb. Here we come across another term, that is Coulomb. Let us understand, Coulomb is the SI unit of charge. So SI unit of charge is Coulomb and is represented as capital C. This SI unit is defined in terms of electric current. So 1 Coulomb is the charge flowing through a wire in 1 second. If the electric current in it is 1 ampere. So what it means? So if an electric current in a wire is 1 ampere, the charge flowing through that wire in 1 second is called 1 Coulomb. To understand more about the size of SI unit of charge Coulomb with respect to the base unit, we are now going to calculate how many base units make 1 Coulomb. We know the equation Q is equal to N into E. So here Q is 1 Coulomb, that is equal to N into E. E is equal to 1.6 into 10 raised to minus 19 Coulomb. Therefore, N is equal to 1 divided by 1.6 into 10 raised to minus 19. That is equal to 1 by 1.6 into 10 raised to 19. That is 6.25 into 10 raised to 18. Look at the size. It requires 6.25 into 10 raised to 18 number of base units makes an SI unit. So this SI unit is very big in practical sense. So in most cases we will take microcoulomb or millicoulomb in our electrostatics. Let us understand one more thing. In this case, let a system consist of N1 electrons and N2 protons. So what is the charge of electrons here? N1 into minus E. And what is the charge of protons here? N2 into E. So the total charge is equal to N1 into minus E plus N2 into E. That can be written as N2 minus N1 into E. Now look at what is N1. N1 is an integer. What is N2? N2 is also an integer. Therefore, N2 minus N1 is also an integer. This means that charge on any body can be increased or decreased also in steps of E, that is the base unit. So that's all about these properties of electric charges. In the last part of this section, we are going to study about conductors, insulators and semiconductors. Conductors are materials that allow passage of electricity through them easily. So conductors allow passage of electricity through them easily, but insulators offer high resistance to the passage of electricity. The semiconductors, the behavior is in between conductors and insulators. So that is one main distinction between conductors, insulators and semiconductors. Conductors allow passage of electricity through them easily. Insulators offer high resistance, that means they are not allowing passage of electricity. In semiconductors, this behavior is in between conductors and insulators. The number of free electrons in conductors are large. In insulators, no free electron, and in semiconductor, number of free electrons are less compared to conductors. Let us look at an example for conductors. They are metals, human body, earth, etc. Example for insulator: glass, plastics, etc. Example for semiconductor: silicon. In our example of frictional electricity, we talk about glass, plastics, etc. Why not any metal? Let us understand the property of a conductor. In a conductor, what happens is, if we put some charge to a conductor, it readily gets distributed over entire surface of the conductor, and if possible it will pass to earth. So if we hold the conductor and applying a charge to the conductor, and if we are in touch with the earth, that charge will pass to earth. So what will happen? So if you rub something by holding it, if charge is created and that charge is passed to the earth. But in an insulator case, if charge is given to an insulator, the charge stays there. As a result, we can observe the charge in that insulator. That is the reason why the frictional electricity is mostly observed in insulators. Let us discuss something more about semiconductors. At 0 Kelvin, semiconductors behave as insulators, but at room temperature, what happens is some electrons free themselves and causes conduction by responding to applied electric field. So at room temperature, they act as conductors. So there are some free electrons at room temperature. In semiconductor, we can also see that when an electron gets it themselves free, there creates a vacancy, and this vacancy created by free electron in a semiconductor also helps in conduction. Now last, we are going to understand what is earthing. We already understood that when a charged body is in contact with the earth, all the excess charge on the body disappears by causing a momentary current to pass to the ground through the conducting conductors. This process of sharing the charge with the earth is called grounding or earthing. So in this video, we discussed about electric charge and its properties. Thank you for watching this video. Keep learning. If you are not yet subscribed to our channel, please subscribe it. Also, please like and share this video.